people show up. So I guess it's a hint that we are starting on time.
Yes, we can start.
Yes, we can start.
Okay.
Yes.
Okay. So hi everybody, we're happy to have Erik Darpö, who is going from Linköping University, Sweden, who's going to speak about non-associative algebras in an associative context. Erik?
Yes, thank you for the presentation, and thank you to the organizers for having me here today. I hope that you can see my slides now. So this is about, well, it is about something that I have thought about on and off for a number of years, but finally some years ago came down to working out in a somewhat more coherent manner. And the basic idea, the basic hope is to try to kind of develop some kind of structure theory for more or less general associative algebras. This may be seen as a vain expectation, perhaps, because one may argue that a general non-associative algebras simply don't have enough structure to allow for much of a structure theory. But well, one can still try and can still see what one gets. So in this talk, I will be working with algebras over some commutative associative ring R with identity element. So R is always a commutative associative unital ring. And when I say an R algebra, I mean an R module A together with a bilinear multiplication map, which of course is not assumed to be associative or commutative in general. For simplicity, I have also added the condition that I want my algebra A to have an identity element. This is somewhat strong condition. The things I will show you, I can do them also if you weaken this hypothesis to saying that you have a right identity element. So an element, the right multiplication with which is identity. I also perhaps have some hope that you will be able to do or tell a similar story about algebras in which there exists a right regular element. And by right regular element, I mean an element such that multiplication from the right with that element is an invertible map. However, in this talk, I will assume all algebras to have an identity element. Yeah. So I already said this, but I already asked the question, is it meaningful to try to develop some kind of structure theory for non-associative algebras in general? And well, I don't know if that is the case. So there were Albert and Jacobson and others who worked in this generality, proved some things in the 40s, 50s, maybe 60s too. But there is very little work in this direction today. And as I said, one may argue that it simply isn't meaningful because there is simply not enough structure to have a theory about. And working simply from the definition of an R module together with a bilinear multiplication, there's very little you can say about such a thing in general just by working with it directly. So what I'm offering here perhaps is, well, it is certainly is not a general structure theory, but it will be perhaps a way of viewing this viewing non-associative algebras in a somewhat new perspective that could perhaps help us to view some of the problems in a different light, and perhaps will allow us to say something new about these algebras also. So the basic idea is that you want to study an algebra A through its left multiplication maps. So the maps, which I will denote by L index A, where A is an element in the algebra, which simply takes an element in the algebra and send X in the algebra and sends it to A times X. So multiplication with A from the left. If you take the collection of all such maps, you get a subset of the set of all R linear endomorphisms, which I will denote by L index capital A. Now the map from A to L index A, which takes an element to its left multiplication map, is an isomorphism of R modules. Right? And indeed, if you have an R module, I mean, specifying such a map is a way of specifying an algebra. If you have an R module A and specify a map lambda into the endomorphism algebra of this R module, that determines an algebra structure, right? However, for us, our goal here will be to perhaps focus on set LA and not so much on the map lambda. So in case A is associative, well, then your LA, the set LA, the R module LA is closed under multiplication, and lambda going from A to LA is not only an isomorphism of R modules, but it is actually an isomorphism of algebras. Right? This is of course very well known. If A is not associative, then LA will not be closed under multiplication, and one may consider, but one may instead consider the algebra, the subalgebra of the endomorphism algebra, which is generated by this subspace. So it is generated by all these left multiplication maps, LA. I will denote that by curly LA, and this is called the left multiplication algebra of A. So this is an invariant, an isomorphism invariant for A, but it is a rather crude one. There are many non-isomorphic, non-associative algebras which have isomorphic left multiplication algebras. However, A is also a module now for the left multiplication algebra, and one may try to use the strategy to study A as a module of its left multiplication algebra and see if the module structure carries some information about the algebra structure of A. So this approach was used quite much in the 40s, in the 50s, as said by Book, Jacobson, Albert, and others. And indeed, they proved some results. The way I'm going is perhaps not exactly the same direction as they are doing, although I'm using the same tools. So we have, since our algebra A has an identity element, we have an evaluation map that takes any element in LA. An element in LA is, well, it's a subalgebra of the endomorphism algebra, so it is some R module endomorphism of A. And if I evaluate that endomorphism in the identity element, that gives me a map from LA viewed as a left module of itself onto A. And henceforth, I will call this evaluation map epsilon, or sometimes epsilon index A, if there is more than one of them around. And by the usual argument, we have that as an LA module, our A is isomorphic to the factor algebra of the regular module of LA, factored out by the submodule kernel of our evaluation map. And from this, of course, we can also see that as an R module, our left multiplication algebra can be written as a direct sum of this submodule L index A with the kernel of the evaluation map. Now let us look at the R module morphism, which I denote by pi, which is simply projection onto LA along the kernel of epsilon. Right? This is an R module. This is a morphism of R modules. And I will define a multiplication, which I denote by star on this space, on this R module L index A. So the elements in here are left multiplications with elements in A. And LA star LB, I denote that. I define that in the following way, that I take LA composed with LB. So this is something that is going to be in the left multiplication algebra. And I project it along the kernel of epsilon down onto LA again. With this construction, it is not difficult to see that our map lambda from A to this LA is an isomorphism of algebras. So L index A with this star multiplication is an algebra, is again a non-associative algebra, which is isomorphic to our original algebra A. And the takeaway from this is that actually I don't really need the map. If I know the left multiplication algebra, if I know this submodule R submodule LA, and I know the kernel of the evaluation map, just as these two, I need to know them only as subsets of LA. Then I can recover A up to isomorphism through this construction of this star multiplication up here. So in a way, if I like an arbitrary algebra, I can view it as an arbitrary non-associative algebra. I can view it as a triple consisting of an associative algebra and two distinguished submodules, this LA and this kernel epsilon. If I have this data, I can recover my algebra A. But this description, although, I mean, there is nothing strange going on here. This is really quite elementary observations. This description, it still leaves a lot of questions. For example, if you have two algebras A and B, which are isomorphic, how are these, the triple of A and the triple of B, how are they related to each other? Is there any kind of way that I can see, given two triples, whether or not they belong to isomorphic algebras? More generally, even, if I have an isomorphism, not an isomorphism, but if I have a morphism, any kind of morphism between two non-associative algebras, A and B, is there any notion of morphism between the corresponding triples that kind of corresponds to this morphism, this algebra morphism? In other words, what I am asking about is there this construction of the triples, can it be made functorial? Is there a categorical interpretation of this observation, which I have spoken about above? And the answer to this is that yes, there is. So I will define a category, which I denote by CR, where R is for the ring, well, and C is for category, I guess, which will capture these triples of the multiplication algebra with its distinguished submodules. So the objects in this category will consist of again, of triples, where the lambda is an associative algebra over my ring R. U is an R submodule, and I want it to contain the identity element. M is a left ideal, and they need to satisfy this compatibility condition that U must generate lambda as an algebra, and lambda should be, as an R module, should be the direct sum of U and this left ideal M. So what I want you to think about, what you should think about here, is your lambda is the left multiplication algebra of some non-associative algebra. The subspace, the submodule U is this submodule LA of left multiplications, and the M is the kernel of the evaluation map. This is how we want to think about these things. So I have defined for you objects. And now morphisms in this category. By morphism from one triple to another in the category, I mean a morphism between the corresponding algebras. So a morphism, an algebra morphism from lambda to lambda prime, which respects this decomposition into subspaces that we have, or submodules. So my morphism phi should send U to U prime and M into M prime. That gives me, that is my definition of morphism between these kind of triples. Alg R, on the other hand, I use to denote the category of all, not necessarily associative, R algebras. And morphisms in this category, of course, is morphisms of R algebras. And remember that I'm working, when I say algebra, I mean algebra with identity element. And I require my morphisms to respect the identity element. So 1 should be sent to 1 by any algebra morphism. And by the way, this goes here also. So when I say algebra morphism phi, I mean a morphism which sends the identity in lambda to the identity in lambda prime. So my category CR, so I said this, we should think about this as the category of these triples. And the morphisms in this, I should think of them as something that corresponds to morphisms between the underlying algebras. And to make this precise, I will construct functors between these two categories. So first I have the functor which I denote by L, which goes from the category of R algebras into this category CR. And it takes an algebra A and simply sends it to this triple we have been speaking about before. So in first position, the left multiplication algebra. In second position, the set of all left multiplications, so the map, all the LA maps. And in third position is the kernel of the evaluation map at the identity element. If I have a morphism between algebras A and B, I will send that to a morphism in the category of triples. And you remember that the morphism in the category of triples is a morphism between these associative algebras which respect the decomposition of this into a direct sum of this and this. So a map here will be sent to a map which I call LF between these two associative algebras. And this, I will define this as the unique morphism which sends a multiplication map LA into multiplication L with f of A inside of the LB, inside of the R module LB that sits inside here. So since these LAs generate the left multiplication algebra as an algebra, it is enough to specify morphism from here to here. It is enough to specify what it does to the generators. And clearly, if I do that, if there exists such a morphism, it is unique. And there is some work here to show that this actually gives you a morphism from here to here, that this morphism is well defined. By construction, it sends the LA into the LB, and it is also not terribly difficult to show that it actually respects the kernel as well. This sends the kernel of epsilon A into the kernel of epsilon B. So when you have done this work, well, then the functor L is well defined. In the other direction, I have a functor which I denote by A, which goes from the category of triples to the category of R algebras. And it takes an object, so it takes a triple lambda UM and sends it to U with star multiplication. And star multiplication for these triples is, well, the same thing as I did before. So U star V. I define this as first I take U and V and multiply them with each other inside of the associative algebra lambda. That will give me something that is in lambda. It will usually not be in this subspace or in this submodule R submodule U any longer. But I project it down along M onto U again. So that gives me an R bilinear map, an R bilinear multiplication on this R submodule U. And if I have a morphism between two triples, I will send that to a morphism which I call A of phi. And since my morphism phi here, the phi is a morphism from lambda to lambda prime, which respects this decomposition. So it sends U into U prime, it sends M into M prime. I will simply view this phi as a map from U to U prime. I restrict the map, and that will be my morphism between these two algebras. Now, it is clear that phi is well defined. It is perhaps somewhat less clear that this is actually a morphism between these two non-associative algebras. But you have to do the work, and it turns out that indeed it is. And then the main result, is that the category of R algebras and the category of triples are equivalent, and that the equivalence between them is given by this functor L and the functor A, which are quasi-inverse to each other. So what this means is that, well, it means, in particular, it means that any morphism in the category of algebras, so any morphism between two non-associative algebras It extends uniquely to a morphism between the corresponding multiplication algebras, and this morphism respects the decomposition into subspaces. So the LA is sent into LB, the kernel of the evaluation map in LA is sent to the kernel of the evaluation map in LB. So this is essentially what we need to prove to show that the functor L was well defined on morphisms. But also the other way around, that if you have a morphism between your multiplication algebras, which respect the decompositions in this way, then you can produce a morphism between the corresponding non-associative algebras by starting in algebra A. You use this lambda to embed it into LA. You apply your morphism phi, now you are in LB, and you evaluate at the identity. So if you compose these three maps, you get the function, a map from A to B, which I claim then is a morphism of algebras. If we started with a morphism phi satisfying these conditions. It also means that every non-associative algebra can be obtained from a triple via this, from a triple like this via this star multiplication, up to isomorphism, of course. And that two algebras are isomorphic if and only if there exists an isomorphism between their multiplication algebras. So an isomorphism here that respects the decomposition, since LA to LA and the kernel of epsilon A to the kernel of epsilon B. This in some way perhaps is not particularly spectacular. It does not really in itself allow us to kind of prove any big results that we did not know before. What it does do, it gives us a different perspective, I think. Instead of working with non-associative algebras, or we can choose to work with associative algebras with a certain configuration of distinguished submodules. And it turns out that everything we would want to know about non-associative algebras can be read off from these configuration of submodules inside of our associative algebras. And well, if you like associative algebras, which I think you should do, this is a kind of a nice perspective. As an application of this, I would like to say a few words of left simple algebras. So an algebra, well, you know, an algebra is simple if it is non-zero, and if it has no proper non-trivial two-sided ideals, right? If your algebra is commutative and associative, a simple algebra is the same thing as a field, but in the associative non-commutative case, there are simple algebras which are not division algebras, right? We can define a left simple algebra as a non-zero algebra which has no non-trivial proper left ideals. In the associative setting, this concept is not particularly useful because an algebra then is left simple if and only if every element has a left inverse. So that's essentially a division algebra. But in the associative case, as one could expect, and as we will see, left simple algebras are like a proper class in themselves, which is significantly different from the class of division algebras. So as I said, A is left simple if A is different from 0, and if 0 and A are the only left ideals. And so a left ideal of the algebra A is the same thing as a submodule of A viewed as a module over the multiplication algebra. So to say that A is left simple is the same as saying that A is simple as a module over the left multiplication algebra. To my knowledge, the first person who studied this class of algebras was Brook in the paper from 1944, where he used precisely this technique. He viewed A as a module of the left multiplication algebra and extracted some properties from there. To my knowledge, also, I haven't seen anyone else studying this class of algebras, which I think is something of a pity. Anyway, let us look at a left simple algebra A, an R algebra, and I will assume, to make things a little easier, that this algebra is finitely generated as an R module. If you have any left simple algebra, or any simple algebra in general, actually, the center of that algebra is a commutative and associative subalgebra. So the center consists of all the elements that associate with everything and commute with everything, right? So the center is a commutative associative subalgebra, and it has to be a field. This is not difficult to show. This result is contained in some paper by Jacobson from the 50s, but also it's not very difficult to prove on your own. Right, so the center of A is a field, and of course A is an algebra over its center. And since the center contains a copy of the ring R, and A is finitely generated over R, it follows that A is finitely generated over the center. In other words, A is a finite dimensional vector space over the center. So it's a finite dimensional vector space over the center. Moreover, one can prove, again, this is not very difficult, that if you have a left simple algebra, then its left multiplication algebra has to be a simple associative algebra. And the left multiplication algebra then is a simple associative algebra, which is finitely generated, so finite dimensional over the field center of A. So by Wedderburn's theorem, we then know that the left multiplication algebra is isomorphic to a matrix algebra over some division ring D. And A is a simple module for the left multiplication algebra. Then we know that the simple modules of a matrix algebra is just a natural module. The modules consisting of all vectors of size n. So A has to be isomorphic to this module. And this division algebra D, it is also not difficult to show that it is isomorphic to the right nucleus of our algebra A. That is, all the elements X in A, which if you put them in a product in the rightmost position in a product of three elements, that associates. So this is called the right nucleus, and the algebra D that we're working with, the division algebra D has to be isomorphic to this right nucleus. So just collecting this fact that the left multiplication algebra is a full matrix algebra over a division ring, and that A then is isomorphic to the simple module for this division algebra, for this matrix algebra. We can apply this to, we can apply our equivalence of categories to this situation to get the following corollary. Yeah, well, I wrote theorem, but it should really say corollary here. So an algebra A over your ring, which is finitely generated over your ring R, we say it is left simple if and only if it corresponds to a triple. So remember that A is a functor from triples to algebras. So it's it corresponds to a triple consisting of a full matrix algebra over a division ring D. So D here is an associative division algebra, of course. U, well, it's a subspace, and M is a maximal left ideal. So D being simple here implies that since this should be the direct sum of U and M, it follows that M has to be maximal. And as usual, U should contain the identity element, and it should generate all of our algebra. Moreover, if I have two algebras A and B, which are isomorphic, well, then first of all, their left multiplication algebras will have to be isomorphic to each other. So if this is given by a triple with the D to the N times N here, then the algebra B will have to be given by a triple with an isomorphic algebra here. And if we have two triples with the same multiplication algebra, with the same associative algebra in the first position, but with different subspace configurations U and M, so DUM here, DVM here, they are isomorphic. These algebras, the corresponding algebras, are isomorphic if and only if there exists an invertible n by n matrix over D, such that conjugation with that matrix sends the subspace U to the subspace V, and sends the left ideal M to the left ideal N. In other words, the configuration with UM and VM, they are the same up to a change of basis. And well, M should be a maximal left ideal, and we know that the maximal left ideal in a matrix in a matrix algebra like this is simply the annihilator of some one-dimensional subspace. So by up to change of basis, we may assume that our maximal left ideal M is the annihilator of, well, some non-zero vector, say the first standard basis vector. So in this case, M will simply consist of all matrices that have a zero in the first column and can have anything else in all the other positions. Then we need U. We need U to be a subspace which is complementary to M. And we can accomplish that by saying, well, the first U has to have dimension N over our division ring D. And also, if I look at all the elements in, if I take all the first columns of all the elements in U, that should generate what I should get is everything there. So U applied to this first standard basis vector En gives me a subspace of Dn, and that subspace should also have dimension n. So this means that U does not intersect M in any way except in the origin. Moreover, we need U to contain the identity element. So I add that condition there. And I need U to generate all of our algebra or of our matrix algebra. One way of ensuring that it does so under these conditions, which I have detailed here, is to say this thing here, namely that that Dn does not have any subspaces which are invariant under U. So if we have two subspaces like this, the corresponding so my left ideals in both cases are the annihilators of E1. Then the corresponding algebras are isomorphic if and only if there exists some invertible matrix which fixes the first standard basis vector and which sends my my subspace U to my subspace V under conjugation. So this gives us, in some way, it gives us a rather kind of comprehensive picture of the class or the category of all finitely generated left simple algebras. So all finite dimensional left simple algebras over some field, right? We need, if I have a left simple algebra over a field, which is finite dimensional, then I know that its left multiplication algebra is a full matrix algebra over some skew field extension of our ground field, right? And all the left simple algebras that have that, they have that multiplication algebra. They are of this form, and we know that isomorphism of algebras correspond to this conjugation with invertible matrices satisfying these conditions over here, right? So I will finish this with an example. We have over any field now, let's just consider any field K. Let A be a Jordan block with eigenvalue 0 for size 3. Let B be its transpose, so a Jordan block in the other direction. And the identity matrix I just denoted by 1. I let U, so what I'm doing now is I want to construct a triple. So the first element in my triple will be the set of all 3 by 3 matrices over K. My subspace U will be the span of these 3 matrices, which I wrote up here. And my maximal left ideal M will be the annihilator of the second standard basis vector. We can now look back if we like and check that the conditions down here are satisfied. So M is the annihilator of E2 instead of E1, but that doesn't matter. If I take my elements in U and apply them to E2, I will get A times E2, that is E1. Well, identity times E2 is E2, of course. And B times E2, well, that is E3. So altogether, they will span all of K to the K3. And as a consequence of that, which I at least mentioned, since M is a maximal ideal, it follows that, well, it follows that this that the full matrix algebra is the direct sum. And it is also, since we have this Jordan block and this Jordan block inside of U, it is also easy to see that there exist no proper non-trivial U invariant subspaces of K3. So this means that this triple corresponds to an algebra which is left simple. And to work out the multiplication in this algebra, we have to compute some products with respect to this star multiplication. So remember that the algebra that we get consists of all the elements in the subspace U, and multiplying two elements in U, we multiply them first inside of our associative matrix algebra, and then we get something that is not in U, but we project down onto U again. So first, if we do that with an arbitrary element in U multiplied with the identity element, well, you multiply them together, you will just get U times 1, which is U. And if you and that is already inside of subspace U. So when you project it down onto U, you get U itself. So this means that the identity matrix, this one, acts as an identity element in our non-associative algebra U star. If we look instead at A star A, so then we take A times itself and project it onto U. So A times A is this matrix here, and we project it onto U, we get 0. And similarly with B star B is a projection of this matrix onto U, and that is 0. And it's easy to see that it is 0 because the second column here is 0. That means the projection is going to be 0. A times B with star multiplication, we take A times B as matrices. It gives us this matrix. And if we project that along M onto U, we get the identity matrix. So projecting along M, that means that I may add or subtract any element inside of the annihilator of the second standard basis vector in such a way that I get an element in U. For example, if I just add a number 1 here, that gives me the identity element, which is why this projection is 1. And similarly, B star A is pi times B times A matrix multiplication. So B times A multiplied as matrices is this. And if we project this onto subspace U, we get again the identity matrix. So writing this down into a multiplication table, we get this. And you see in particular that it's an algebra with the identity element. We knew that already. But we also notice that it is commutative. It is, and many of you will probably recognize this as a Jordan algebra. Right, so this is left simple, but also commutative, which means, of course, then simple. So this is a simple non-associative algebra. Somewhat more general, I will do a similar construction inside of the algebra wall n by n matrices. So let A be a Jordan block with eigenvalue 0, looking like this. And for I equal to 3 up to n, I let Bi be the matrix which is 0 in columns 3 up to n, but in the first column has a non-zero element, has a 1 in position I minus 1, and in the second column has a 1 in position I. I let U be the span of a matrix A, the identity matrix, and all these B's. This is a subspace of our matrix algebra, which turns out to be supplementary to the maximal left ideal annihilator of E2 again, so similar to last time. Which you can check that everything is satisfied, and the algebra that we get from this construction looks like this. Again, it is commutative, as you see. Funnily enough, the product of any B with any other B is 0, but A times any B is non-zero. So this, again, you see this is an algebra. It is left simple for the reasons we spoke of. It's commutative because you can see this. This generalizes if you insert n equal to 3, you get precisely our previous example. However, this is not a Jordan algebra if n is 4 or more. So one thing that this example shows you is that over any field, we can find a left simple algebra or even a simple commutative algebra of any dimension we like. I'm pretty much done with my material here. What I would like to comment perhaps is, so if we want to say something about like non-associative algebras in general, perhaps one natural step would be to think about, can we understand in some way simple algebras? And then we look back at the associative case where we have Wedderburn's theorem, or Artin-Wedderburn's theorem, which tells us that any simple associative algebra is a matrix algebra over a division algebra, over a skew field, right? So in the associative theory, the step from division algebra to simple algebra is kind of easy. You can get any simple algebra as a matrix algebra over a skew field. So the challenge there is to classify all division algebras. And you might ask, is there a similar way, or is there any way in the non-associative context to construct simple algebras in some way from division algebras? And I don't know the answer to this. I would love to know, but I think so. I mean, in general associative setting, division algebras are kind of difficult to work with. The division condition is not very nice at all. I have a feeling that if you want to find some kind of non-associative version of a Wedderburn's theorem, or in general any kind of construction of simple algebras from some smaller class of algebras, maybe you should not try to construct simple algebras from division algebras, but maybe you should try to construct simple algebras from left simple algebras, so that the from the point from some perspective, perhaps the correct non-associative analog of division algebra is not non-associative division algebra, but non-associative left simple algebra. And this is one motivation for why I think left simple algebras are interesting and worth to study. Thank you for your attention.
You? Are there any questions? So I have a question concerning the last comment that you had. So, of course, you want to somehow mimic. First of all, I really like the fact that you can translate things to central simple algebras and then work your way back to left simple non-associative algebras. I think it's pretty cool. But now, when you try to mimic the theory of central simple algebras in the associative case, you have also Morita equivalence, you have Rao equivalence. Is there anything, not necessarily having a division algebra at the bottom, but any idea of Morita equivalence in the non-associative setting?
Well, I mean, really no clue. I mean, Morita equivalence means equivalent module categories, right?
Right.
So if you want to, if you want to speak about Morita equivalence in the general non-associative setting, you would have to first tell me what modules for general non-associative algebras is supposed to mean, and I really don't know that. Of course, there could still be some kind of some kind of similar notion, but I don't know. I don't know.
Or you could do, then a naive approach would be to just take matrices over non-associative algebras and see what you get.
Yeah, maybe.
Seidon, do you have a question?
Yes, thanks. Thank you very much for the talk. So if I understood correctly, if you start with an octonian algebra, the curly L of A is simply the full 8x8 matrix algebra.
Yes.
And then so then you probably have a bunch of other algebras that have this property, including the full 8x8 algebra itself, which is associative. But is there a way of saying, like, okay, which algebras are in this sense close enough to being octonian algebras somehow? I don't know if that question is well defined.
Well, I mean, if close enough means sharing the same multiplication algebra, basically all of them.
Right.
Right. Basically any, I mean, so basically any like left simple 8-dimensional algebra will have the full matrix algebra as its left multiplication algebra. There are only some kind of rather rare cases that will have something small.
But then can you limit these distinguished subspaces?
Sorry?
So can you limit these distinguished subspaces in a way that you get a finer notion of what close enough means? Or
yeah, well, I mean, I guess you could. I mean, one closer notion would be to say that, okay, we have the same vector space to start with, or the same R module if you want to work in that generality. And with different algebra structures on the same vector space. Then of course one invariant, which is in general finer than the multiplication algebra, is the set of all the left multiplications. So the set of left multiplications together with the map from the vector space, that is the algebra structure, so that's everything. But if you forget about the map, but remember the space, which I called U in my triple, or L big A.
Mm.
That will give me something that is a finer invariant. And I'm not completely, I'm not completely sure. That may, at least for division algebras, I think that may recover your algebra up to isotopy.
Okay.
I'm not sure about that, so don't quote me on it. But something along those lines.
Okay. Thank you very much.
Any other questions? Okay. If not, let's thank Erik again.
Thank you.
I suppose we resume next week. Bye,
Yes.
guys.
Thank you all for listening.